Hi, welcome to the Signal Path. In this episode, we're going to try another repair. What I have here at the bottom is an Agilent MXG vector signal generator. This is model N5182A, and it's a 6 GHz synthesizer with a built-in dual DAC, allowing you to apply any kind of arbitrary waveform directly to an IQ modulator on an RF carrier. So you can do really cool and interesting things around the carrier, useful for a whole bunch of ISM band application. Now, even though it's fairly old, it also has a pretty good phase noise. So if you can fix it, we should definitely try. I have its output preemptively connected to the input of our Siglent spectrum analyzer here. This is a real-time spectrum analyzer, model SSA 5085A, up to 26.5 GHz. Really compact, really quiet, with a lot of features. So it's going to be fun trying to fix this using this instrument. So right now I have it set to 5 GHz and 0 dBm. And you can see that the tone applying over here is showing up perfectly. So it's working quite nicely. We're not measuring phase noise or anything yet, but at least it is doing the right thing. The power is correct. So the ALC loop is also working. Let's go ahead and increase the frequency, going all the way to the highest frequency. Here you go, 6 GHz, still shows up quite nicely. Let's go the other way. So here is 5, and let's go slowly down. Oh, there you go, look at that, it just disappeared. And over here, an error has popped up, which says a Fractional-N PLL has been unlocked. In fact, this unlock is so catastrophic for this PLL that the frequency has completely disappeared because it's probably sitting somewhere and it's not passing through the bandpass filters for this particular frequency this is trying to generate. So you're seeing nothing at the output. Let's keep going down in frequency. Let's see if it ever shows up anywhere else. Right now we're at 3.1 GHz. There you go, look at that. It showed up again. And we're going further down. It's still there, and then it disappears again. So we can go back and forth a couple of times and find out which frequency ranges it works and which frequency ranges it doesn't work. Now, one thing we can do to get a good idea is to set a sweep on this. We can do a sweep across the entire frequency and then put this thing into continuous persistent mode so that it never clears up. For example, I can do a max hold. And then if I do a max hold over here, we can go over here. I've already set up the sweep, and I can turn the sweep on and let it go. There we go. So as it tries to go through, it's going to be locked and unlocked in various locations, and we will be able to catch it. So you can see it's working in a couple of places here, and it should pop up here again. There it is. It pops up, and I think it's going to disappear again. There you go. It's gone now, and then it's going to pop up here somewhere else again. I think it's towards the end. It should come back. Let's see if it comes back. There it is. Look at that. Now we have a whole bunch of bands where this thing is working and not working. Okay, let's disable the output. So now we can use this as a guide and figure out what could have possibly gone wrong in what part of its internal fractional-N PLL, which is very complicated. Now, there is a lot of nuances when it comes to PLL analysis and PLL debugging, especially because depending on which direction you're sweeping, you're going to get a different reaction from the PLL. That's what happens when PLL gets unlocked. There is a hysteresis in there, depending on the direction in which you approach it. So this is all going to have to be taken into account. But at least this is a little bit of a guide. We can use this picture when we look at the block diagram of this instrument and see if this makes any sense. Now, we do have the complete block diagram of this instrument. Unfortunately, there is no detailed schematic, but even from this, we can get a good idea of the signal path, pun intended. Now, everything that is in yellow here is actually on one board. This is unlike some of the other instruments where every one of these sub-functions is on a different card, and this has to do with the cost performance metric of this class of instrument. Now, in the service manual, anything that goes wrong, they say replace this board, which replaces everything at the same time. Keysight doesn't do component level repairs anymore, and many other companies don't. They just throw this entire board away. But of course, we don't want to do that. We want to look at the individual components. This section here in the middle that's in blue, that's a different card. This is not the problem anyway. This is the IQ modulator section. We don't really even need to look at it. Now, if you look at the top level from here, the fundamental functions are actually written. It's pretty straightforward. We have the reference that generates the key reference inside the instrument. The synthesizer VCO fractional-N, that seems to be the problem part. And then we have some multipliers and dividers, and then the RF section, which is just amplifiers and path selection. And there's the entire ALC here on the right corner. The ALC is probably working because we saw that it has producing a very, very nice flat output, so this section is okay. Then when you run the self-test on this instrument, it's going to generate a whole bunch of errors, including errors on the ALC. And that's because when the output disappears, the ALC just simply saturates, and it thinks that it's not working. But in reality, there is no signal. So most of these problems that we see, they're all essentially related to the fact that the synthesizer gets unlocked. So we really need to dive in and understand how all of these things work together. And since this is a synthesizer problem, we should look at the reference synthesizer subsection and see how these actually work together. So let's zoom over here around the reference section and see what the reference is actually doing. So we do have the input from the outside of the instrument from 1 to 50 megahertz, and in here somewhere, there it is, we have a 10 megahertz VCT CXO, and that's going to be the primary 10 megahertz reference of the instrument. There's also a 100 megahertz oscillator over here, which is in its own PLL through this path over here, and that's going to lock this 100 megahertz internal oscillator to the VCXO at 10 megahertz, and that's going to then inherently generate 50 megahertz, which is a divided by 2 version of this, a 500 megahertz, which is a times 5 version of this, and a 1 gigahertz, which is times 2 of the 500. So at least I think that this guy, this one, and all of these are probably fully functional. And this 1 gigahertz is required for the heterodyne down conversion for the lower frequencies. We will see that. We don't have to worry about this right now. But if any of this section wasn't working, it would generate a reference unlock condition because this loop would be unlocked, but it's not doing that. Ironically, this would be a much better place for the problem. This is actually a lot easier to fix. Everything is lower frequency. Most of it is off the shelf, whereas that stuff at the top is very much custom. So let's go over here and see what the actual problem is. So the PLL Fractional-N Unlock condition comes from this one. Now, at the heart of this synthesizer, there is a custom-made VCO using discrete components, and that VCO operates from around 750 megahertz to 1.5 gigahertz. So all the frequencies that are generated inside of this instrument rely on this range of this VCO, and they get there by heterodyne, division, and multiplication to cover the entire 250 kilohertz to 6 gigahertz. It's all based on this. And when this is unlocked, you have essentially nothing. And if you look at this, we do have an integrator over here as part of the PLL loop, and then we have this section here. Unfortunately, this section is completely custom made. It's made of a combination of FPGAs and some fractional N dividers that they just run delta sigma on in order to get any fractional divisions they want. And this section, some of these components, we will not be able to fix unless we find an exact replacement, if indeed the problem is over here. There's also FM ADCs and so on and DACs for some of the other modulation you can put on top of that. It's very common to inject various FM modulation into the loop of a PLL in order to accomplish what you're looking for because you're within the loop of PLL bandwidth. Anyway, we don't have to get into the details of this to worry about it, but for every synthesizer VCO fractional combination, we're going to need the output of the VCO. Then we need the feedback where this is actually locked into. So if you follow this, you can see that this signal, which is the VCO output, goes up here. Some of it is coupled into another path, probably used for something else, and then it gets doubled. So interestingly, that 0.75 to 1.5 gigahertz VCO signal directly gets doubled, and it goes through a bank of filters to get rid of the harmonics. And the 1.5 to 3 gigahertz signal is coupled again to the top, but then it's also fed back. So there it is. That's our actual loop. We can draw the loop on top of this. Exact loop condition is from here. The VCO goes over here, goes through the doubler, goes back here, and there is your loop. And that's how you close the loop, of course, with the charge pump and everything else in the middle. So if this loop somehow doesn't work, any component of this loop not working is going to give you that fractional and PLL unlock condition. So that's where we need to pay attention to. Now there's a bunch of other stuff over here. We don't have to think about that right now. But if you look up here, the signal that is coupled here goes through dividers. So that's going to generate signals that are below even the VCO frequency, so that's division, and then the doubled, and then it gets selected between the two. Now, between this path and this path, we cover 0.25 to 3 gigahertz completely. That still doesn't go lower than 0.25, that's 250 megahertz, and that's done by heterodyne. And then it's doubled again. Now the signal over here can cover from 0.25 to 6 gigahertz. Now everything below 0.25 comes from somewhere else, the heterodyne section. Where is the heterodyne section? Here it is actually. There you go. So then if the 1 gigahertz reference comes over here, this gets mixed in, and then 100 kilohertz to 260 megahertz then gets covered here. So we have the high band, the low band, and the heterodyne band all combine and go to the output. Now there's a lot here. We don't actually have to really worry about this because all this stuff is really working, and as long as this section is not generating the correct frequency, nothing else can happen. Because if you look at this, that signal all comes from these sections. So there are a couple of the multipliers and so on in there that we need to also be wary of. But it looks like that even though the VCO frequency is from 0.75 to 1.5, the signal being fed back to the VCO loop, the Fractional-N, is the double of that frequency. So we have the multiply and then division again. I'm not sure why they've done that, probably for the phase noise reference performance and everything else, and for whatever fractional divisions they needed, they required this. Now, just to make sure that the reference of that Fractional-N comes from here, the 50 megahertz reference, which is coming from here, which is most likely itself is working. This 50 megahertz reference, if it wasn't working, you would never be able to lock this PLL in any frequency range. Nonetheless, we can measure this because this is a fixed frequency, unlike the one that's coming back here that when it unlocks, it jumps all over the place. Now, analyzing PLLs in a closed loop is an absolute pain because once the loop is unlocked, everything gets saturated to one side and it jumps out of the range. But that is what we have to do initially before we start breaking the loop apart and figuring it out. So let's go and identify all of these components on the main board before we make any measurements. I almost forgot to look at this measurement section that we had done. Now with the information we have about the block diagram, we can make sense of this. Remember that the VCO is supposed to work from 750 megahertz to 1.5 gigahertz. And that's in fact exactly this section right over here. You can see that it doesn't work in its entire section because 1.5 gigahertz is right here. So in the upper range of the VCO frequency, it seems to be kind of working. But once it goes below about 1.2 gigahertz, the entire fractional-N gets unlocked. 1.2 gigahertz is right here. Every one of these divisions is 600 megahertz. Now, if you look at this section, this is just this part multiplied by 2. So no wonder that this section is also working because that's just a doubler range of the VCO. As long as the VCO is locked within that range, the double frequency seems to also be working. And then this section, which is even wider, is also the double again. That's why they keep getting wider and wider because you're doubling the frequency, so the range in absolute value is increasing. So double over here, double over here. So these are all really the same signal, just multiplied. And this section over here is the divided version of this, which is also working. And there's a tiny little bit here at the bottom, which is a heterodyne section. So these are all really the same thing. This should be able to go further down. And if this does go further down, then this will be able to go further down. And then these guys will all be able to go further down. So yeah, this entire range is definitely not working. And the VCO only gets locked in a small portion of its entire range. And all of these measurements are really connected to each other. So it all really actually makes sense. And here is the main board that's responsible for all the functions we talked about. As you can see, it's quite large, and not only does it have everything that we saw in that block diagram, it also occupies essentially the entire backside of the unit. Now, there are multiple covers on top of this which I've already taken off, particularly the really big compartmentalized divisions between these sections where you can see the exposed metal. That big piece on top of this has also been removed. Many screws. This provides isolation and everything else between the different sections. So looking at it from the top, we can actually quickly figure out what each section is for. And then from there, we can hone into the area we are interested in. We see over here sections responsible for that initial reference generator. Here's our TCXO, and there must be some over here, most likely on the other side, the actual oscillator, the 100 megahertz oscillator. So that portion is working, so we don't really occupy ourselves too much worrying about this section. Over here is the entire output section. You can actually see the individual paths for the low band, high band, and the heterodyne band, all of them converging ultimately into one path and going through 3 custom ICs at the very end, reaching to the output, most likely the power amplifiers, and possibly maybe some of the final mixing stages and ALC and all that in that area. Again, that section is working, so we don't have to really worry too much about that. There's some crazy budge over here as well. There's some digital stuff in this corner. Again, nothing to worry about. The portion that we need to pay attention to is where the VCO is, because that's the fractional-N loop around it. If you look very carefully, and I'm going to zoom in so we can talk about it in more detail, our VCO is right over here. This little section is our VCO with discrete components, that amplification area right after it, and then the signal is fed through here and then finds its way back through this section. And here is our fractional-N divider, here's our phase detector, and then back in here to control the VCO. This FPGA is controlling this. The combination of this guy, this guy, this guy, and the loop makes the fractional-N PLL. There's also a couple of additional hints, because over here there are ADC and DACs, which are responsible for the FM modulation. We saw that in the block diagram as well, feeding it directly into the loop. It all has to be within proximity. So the loop of the PLL is essentially this path over here. So we have to pay attention to this. And there's a couple of other bandpass filters you can see with switches in between them. These are using LC components, so probably the lower band frequencies. And there are a lot of other filters embedded inside of the PCB which we don't see. For example, these sections over here have tons of bandpass filters. We've actually done x-rays of these kind of boards before, and we know that how they're making those. They're embedded in between the layers, and that allows them to, first of all, not radiate out, as well as really retain the space, because you can put additional things around it if you need to. So it kind of all makes sense. So let's take a closer look over here so we can see which areas we really need to measure to see what's going wrong in this loop. And now with a closer look, we can analyze this circuit a little bit better. So starting from the VCO right over here with the discrete components and diodes used as varactors, we can even see a little label over here with a test point. That's the bias. That's most likely part of the loop. It's controlling the frequency of the VCO. The output goes over here. There is an amplification stage and then jumps to this section. And if you remember from the block diagram, here is where they split it off. So one goes off to get divided for the rest of the frequency, and the other one actually gets doubled as part of the primary path of the fractional-N as well as the actual functions. And I think that doubler is right over here. We can see that they steal some power using a pair of these transformers, so they basically couple some away. And then at this point, it looks like they're differentially driving this, maybe just a diode actually, creating the double signal. And then what comes out is single-ended. So this is pretty tricky because the doubler is in this entire tiny little section. And then it goes over here. This is a switch, and this is a switch, and there are in between them multiple bandpass filters, which we saw in the block diagram. They're all buried inside. This chip controls this guy, this chip controls this guy, 2 bits to control them, and then that entire section makes up that doubler and filter. And then over here, they do something interesting. They split it off just using a resistive splitter. We saw that in the block diagram as well. They just tap it off, basically. And then it goes up here, and there is more multiplication. But we're not interested in the path going up anymore because that goes back into the actual RF output. Over here, there is the path outside of this, which then passes everything down into here. And this is our Fractional-N. It's a custom part by On Semiconductor, which is made for Keysight, I think. And then from this, it goes to the phase detector. The 50 megahertz input also reaches the phase detector, which we know works because that comes from all the way on the other side. So the 50 megahertz, that is the loop, closed loop 50 megahertz and the fixed 50 megahertz, both going to the phase detector and then comes back over here. And I think this op-amp is part of the integrator, which then controls the VCO. So we have VCO, coupled path, doubler, bandpass filter selection with 2 switches, fed back, input of the fractional divider controlled by the FPGA, phase detector with the 50 megahertz reference, and back into the VCO. And that's the loop we really should be paying attention to. Now what we can do is we can actually run this. Luckily everything here is on the top, and we can probe these different areas while the loop is working and convincing ourselves that these signals really are where they are supposed to be and they do travel through this entire path. That's pretty easy to do with an active probe. So we should be able to make these measurements, and that really should be the first step. And here's the first setup we're going to use to analyze and understand the circuit. So the instrument is turned on, and you can see there are actually LEDs inside of these custom Agilent packages, and they glow when you turn the unit on, which is always kind of funny to see. Right now, the instrument is set to 2.5 gigahertz. Now, most of the time, the Fractional-N loop and everything works at 2.5 gigahertz. Now, based on the block diagram, we know that that means the VCO should be running at 1.25 gigahertz. We have a doubler, we have the entire loop into the fractional division and everything else, and we should be able to monitor those signals to see if they are actually where we think they are. And that's going to help us at least understand the circuit in part of our reverse engineering. We do have an active probe over here, which is powered by this power supply over here. The output of the active probe goes into the Siglent analyzer just like before, and then we have the tip of it, which we can use to poke around in different areas over here. So let's do some measurement and see if it makes any sense. So I went ahead and I changed the frequency of the instrument to actually 2 gigahertz rather than 2.5 because it was too close to all the Wi-Fi and Bluetooth activity that you can see around here. The reason all that couples to the output is because, of course, there's no cover anymore. The instrument is completely open and it's a huge antenna, so it's going to pick up all kind of garbage and it's going to interfere with what we want to measure. So that's why I moved it a little bit further down. It still logs perfectly fine at 2 gigahertz. So you can see the output. This is now directly from the instrument output, and yep, we do have the 2 gigahertz. We have the power that is correct. Now we can switch to the probe and go to the different sections. All right, so first thing first, is the VCO output really at 1 gigahertz? So let me go ahead and probe directly the output of the VCO. Here's the output of the VCO, and check it out. It is exactly at 1 gigahertz. Now it's going to have a little bit of harmonics in it. That's normal because the VCO is putting out quite a bit of power. And yeah, indeed, we have exactly what we expect. So let's follow that a little bit to the other side and see if it reaches all the way to before the doubler. It was right before a doubler. Yep, right before a doubler. You can see we still have a very strong 1 gigahertz signal there. And what about right after the doubler? Is the doubler actually doing what it's supposed to do? And look at that. There's our doubler. So the doubler right after the VCO indeed does produce that. And the power is now quite a bit smaller because it does need to be amplified. Now let's follow that to see if it goes in the switch. Yep, there it is. It goes into the switch after the amplification. The signal is also much larger. You can see there is a little bit of fundamental leakage, and of course the harmonic there is there as well. And does it come out of the switch? Okay, that's coming out of the first switch. Yep, it's indeed there. Does it go through the filter and come out of the other end of the switch as well? Yeah, look at that. It does. You can see it's so much cleaner. because it went through the filter. See, let me going to measure before the filter. Here's before the filter. Look at the fundamental and look at the other harmonic, and here's right after the filter. Significantly cleaner. So yeah, the filters are also doing what they're doing. Now remember, this is only one of the paths of the filter. There are multiple filter paths. We're just selecting one because the frequency is fixed. Now does that reach all the way to the input of the divider? Yeah, there it is. The input of the divider is also there. The signal is quite a bit smaller. There's a lot of loss there. I'm guessing that's normal. So what do we have right before here? Goes from -20 with a long trace in the PCB to around, yeah, that's you know, also my grounding is not perfect. No, it's fine, it's fine. There's a little bit of loss, but it's not too much. Now on the other side, we should see 50 megahertz coming from the actual reference. There it is. That is not 50 megahertz. What am I saying? You're not going to see 50 megahertz here anyway. We're starting at 600 megahertz, so it's way, way down there. So if I change the start frequency to, let's say, 1 megahertz, over here, there it is. Okay, the 50 megahertz is there. I was just looking at some weird harmonics. And the other side of the phase detector, there should be another 50 megahertz. And that is over there as well, all the way in the left. Okay, so everything is there. That this shape that you see is because of the fractional behavior. Okay, all of that looks good. So in this frequency range, it's actually working correctly. So let me put the start frequency back to 600 megahertz here so we don't see. The reason, by the way, I've chosen 600 megahertz is because my wireless microphone is around 512 or so, and that's going to show up because it's being picked up as well. So we don't want to see that tone by mistake and confuse ourselves. So once again, let's look at the VCO output. If I can find it again, where are you, VCO output? There's the VCO output. Very strong, nice 1 gigahertz signal. So right now the instrument is set to 2 gigahertz. If I go up, let's say 10 megahertz and down 10 megahertz, this should move by half of that. So let's try that. So here's up 10 megahertz. Look at that. It moved exactly by half of that. And here's down, and it works fine. So around here is perfectly locked, and it has no issue. If I go to the doubler output, that doubler output will follow exactly the frequency. Here we go up by 10 megahertz and down by 10 megahertz. It works. So let me slowly change it and see at what point do we lose it. Let's keep going down. So 1.99, 8765, 4321. Oh, and it disappeared. But it disappeared exactly at 1.9 gigahertz. That's interesting because 1.9 gigahertz was one of the filter bank divisions. So let's think about the significance of the measurement we just did. So we looked at the VCO output frequency here, and it looked just fine. We also saw the coupled path, and that was okay. We measured the doubler after the amplifier. That was okay. We looked at the signal after the filter bank, and we saw that its harmonics got better. So at least this path, where we had it selected around 2 gigahertz, was functioning perfectly fine. And then we looked at the signal coming over here, which is the one that's going directly into the divider. And that one seemed to be okay too. Now, right around 1.9 gigahertz, when we were crossing that barrier, it became unlocked and the VCO frequency completely disappeared. Now, that happens to coincide with exactly this transition. Now, this doesn't necessarily mean that it's exactly at that frequency. That's something that we have to verify experimentally and see where these switches happen. Now, it's more than just the fact that maybe one of these filter bank is broken or the switch is broken, because there's also a dynamic characteristic. When you switch from one filter bank to another, there's a brief moment when the loop is open, and this whole instrument, perhaps using the pre-tune and every other thing in here, has to calibrate and coordinate that so that the synthesizer comes back online as quickly as possible and retains the lock. So from an end user point of view, it looks continuous, but it's actually not internally continuous. So one thing we can do is we can actually break here and break maybe here, and then measure this section on its own. Basically measure the S parameter of this path, and then as we dial the frequency selection, it would actually jump between the different filter sections, and we should be able to see these bandpass filters jump between the individual bands. If that section works, at least we can say that this area of the filter switching, at least the response is correct. I think we should be able to remove some capacitors and put some cables in and actually measure this section in isolation before we get into any other area. And so I've gone ahead and removed 2 of the series capacitors on the board, and I'm using those pads to attach 2 coaxial cables directly in their place. Here's the input of the filter, here's the output of the filter, and the switches and everything, plus the amplifier is now in the path. Now this allows me to also scratch a little bit off the silk screen to connect the ground of this coax. This transition isn't going to be perfect, but it's going to be good enough to see if everything is working. At least the relative response between all the filters should look good in this case. Let's give it a try. And here's the setup to measure the response of the filters now with the cables attached directly on a network analyzer. We're going to be using the Siglent SNA5014A, which is a 4-port 8.5 gigahertz network analyzer. I've done a complete teardown and review of this instrument, and I've been using it quite a lot since then too. It's really nice. It has some really nice options. There's multiple videos on that you can catch. So here you go. So the two cables are directly connected to port 1 and 2. I've calibrated to the edge of these cables using an eCal module. I'm using the Keysight one over here. And that's it. We should be able to see the response once we turn the instrument on. And here we go. The synthesizer has been turned on and it's set to 2 gigahertz. And check it out. Looking at S12 here, this depends on the way I've connected the ports, we see a bandpass response. And this matches exactly that middle filter. So indeed, it is working. Now what I can do is I can adjust the actual frequency of the synthesizer, and at some point it should switch to the other band. So let's go down towards the area where it became unlocked last time. So if I go down here, so it's 2 and here's 1.9. I know it hasn't switched yet, which means that that was just a coincidence. If I go to 1.8, yeah, there it is. So now it switches at 1.8 gigahertz. So the fact that the synthesizer became unlocked at 1.9, that was not the transition of the filter directly. The switches were still in the original position, so it had nothing to do with the filter. But that's an interesting to learn. If I go back to 1.9, it goes to this one. Now if I keep going higher, eventually it should switch to another one. There it is, and here's the higher band. And you can see all of them have roughly the same response. They all have the same gain. So yeah, the switches and the filter, I think they're okay. Well, it was a good thing to try. At least it was in the past. We can eliminate it as an unknown. But yeah, the issue is not the filter bank nor the switches. So now that we have verified the filter bank and the switches and everything is working, we should turn our attention here to the bottom and change our strategy a little bit. Now, one thing that can happen to VCOs is that they can lose the ability to sustain oscillation across their entire desired tuning range. Now, typically speaking, this happens on the upper frequency ranges, not on the lower, but it can happen either way depending on what goes wrong. So in this case, we know that this VCO and the loop works around a 2 gigahertz output, which is a 1 gigahertz VCO frequency, but once we go below that, it stops. So perhaps it just can't sustain oscillation below 1 gigahertz. And this can happen because if the varactors are not working properly or something has shifted or aged. So in that situation, what we should do is we should break the loop. So what I can do is I can come over here, find this node, and override it with an external voltage. And once I do this, now I control the tuning voltage of the VCO independent of what the rest of the system is trying to do. And then I can go ahead and measure this signal, for example, and see if I can tune the VCO across this entire desired tuning frequency. And that's going to tell us another piece of information. If it doesn't sustain oscillation at lower frequency, then we know the VCO is indeed the problem. So let's try that. And here we are at the bottom. So the VCO is over here, and the control circuitry for controlling the voltage on the VCO's varactors is over here. And the tune voltage is actually right there. Nicely, there's a clip there we can attach to. And this voltage is coming from another power supply. I'll show you. This has about a tuning range of about a couple of volts to about 15 or 16 volts or so. We can just travel through that range and look at the output of the VCO and see what frequency it is producing. It doesn't matter what the rest of the loop does, really, because all we care about is to see if the frequency range of the VCO can be covered. And we're going to connect it to the spectrum analyzer with an active probe to measure that. And here's the setup again. You can see all the way in the back, I have the Roden-Schwarz source measure unit there is providing 14 volts right now, overriding that voltage. And you can see that it is drawing a couple of milliamps, of course, because the op amps inside of the control circuit are also trying to write into that voltage, but I'm coming in with a much lower impedance, so therefore I can override it. And the active probe is connected to our spectrum analyzer once again. Let's take a look at the VCO tuning frequency range. Okay, here we go. I'm probing the output of the doubler again. So remember, the VCO frequency is half of that, and we know we can lock around this frequency. Let's go ahead and step this down and see how far it goes. There you go. Look, I can easily tune the VCO quite nicely. Let's tune it further down. So we were okay here. There's a little dip, but that dip is just because of the way I'm probing it. That's not really from the circuit. And let's see. And look at that. Yep, the VCO has no problem. It should go all the way to 1.5, and it does. Yeah, even goes below that. So yeah, the VCO range really does cover everything. Yeah, that's not the problem. Oh, that's a shame. So the VCO works perfectly fine. And yeah, it anyway locks here perfectly fine. All right, well, that was a good thing to try, but this tells us that the VCO is okay. Yeah, it definitely goes as low as that. So it doesn't unlock because the VCO can't cover this frequency. There must be another reason. All right, back to the block diagram we go once again. So we have verified the VCO as well. So most of the things are verified. Unfortunately, we're getting closer and closer to the custom chips from Agilent, and that's going to make this unrepairable if we can't replace them. So let's take a look at what is left. So we know that it works in some frequency ranges. So this divider, this custom divider circuit, the phase detector, they do work in some places, but just not in all other frequency ranges. So perhaps this divider's ability to actually divide in a fractional N mode around the frequency of, let's say, 1.4, 1.5 gigahertz, it just doesn't work anymore. Well, we can actually verify that by overriding the VCO frequency once again. So what we can do is we can override the VCO frequency, put this frequency at, let's say, 1.6 gigahertz. We know it doesn't work at 1.6 gigahertz. And then we can go ahead and tune the actual synthesizer and ask for 1.6 gigahertz. So think about what happens in that situation. If I'm giving a 1.6 gigahertz to the divider, and this is asking for 1.6 gigahertz, what it's going to have to do is that it's going to do a fractional N division such that the output of this divider is 50 megahertz, because it's always covered with this 50 megahertz reference. That's how the loop actually works. So this fractional N chooses a division ratio such that 1.6 divided by that division ratio becomes 50 megahertz when you're asking for 1.6. So essentially we can force it near its own locking condition and make sure that this guy can divide and produce a 50 megahertz. If this guy does produce 50 megahertz and that tone does go up and down by adjusting this frequency ever so slightly, then the divider is also working. Then there's really only one other thing left, which is a phase detector at that point. And of course the circuitry here. So let's try that, see. That's a little bit of a tricky measurement here, but I think we should be able to do it. I'm going to set it to 1.6 and do the things I just said and see if 50 megahertz comes out. So now we're talking about this part of the circuit. This is our fractional N divider. At this input over here, we have a single-ended signal coming in from the feedback path. This goes up to 3 gigahertz. That's the VCO frequency times 2. What comes out of here is going to be a differential signal, which is converted to single-ended. That's a divided signal, and that goes into the phase detector. That's what has to be 50 megahertz for the loop to be locked when you're asking for the desired frequency. And then on this side comes the reference 50 megahertz, which we know works. It comes from the reference circuitry. So we're going to look at this one and this one, and then ultimately the output of the phase detector. So if everything is working and the divider is working and can divide when this is at 1.6, we should be able to see something close to 50 megahertz on both of these things. Let's measure that. Okay, I've adjusted the VCO manually to be around 1.6 gigahertz. The synthesizer is set to ask for 1.6 gigahertz. Let's take a look and see if it makes sense. So here's first the reference going into the phase detector. We know this works and this should be exactly 50 megahertz. There it is. And it looks perfect. Now let's look at the divided signal. And what do we have? Oh man, it's really close. No, that looks good. So that's not the issue. But let's see if we can move this. We should be able to move this by adjusting the VCO frequency a little bit. It should move at the division ratio, of course. Let's see. Yeah, I can move it. No, the divider works. Look what happens when it gets really close to locking. There you go. So even all of that is working. Oh man, that's a little unfortunate. I was really actually, maybe I wasn't really hoping that this would be the case, because I don't know where I would find the replacement chip. Let's look at the output of the phase detector now. Now in here, we should see both of these tones actually next to each other. Do we see that? Look at that. Here it is. So the one in the middle, the one that the marker is on right now is the 50 megahertz. So look, I can move that. So this is an unlocked condition when we are above the carrier frequency. Here is right on top of it. You can see they coincide at some point. And then here's below. Wow, it works. All right, well, there's not much left. Everything else looks pretty good. Yeah, so, all right, well, the divider is working at 1.6, so that's not our problem. This really verifies the majority of that loop. So what else is left? Well, there's only a few things. The detector itself could potentially be a problem, and all the analog circuitry following that. So now we did verify that this fractional N divider, at least at 1.6 gigahertz, produces the correct 50 megahertz output, even though the entire synthesizer doesn't lock at that frequency, and that says something potentially, at least at that point. We also looked at the output frequency, 50 megahertz. We saw that we could move it. We looked at both of the tones at the same time. So all of that looks roughly okay. Now, somewhere on the obscure corner of the internet, I did manage to find the data sheet for the phase detector itself. It is an Agilent part. Part number is 1GC14218. It's a gallium arsenide phase detector, and it's a 100 megahertz part with fairly good 1/f noise and noise floor and so on, which you would expect from something like this in a synthesizer feedback circuitry. And if you look at this, this also has a gain that 0.33 volt per radians, which I think is actually adjustable. Now, it is a gallium arsenide part with a negative power supply. Now, there is a theory here that maybe this has degraded to a point where the gain of the phase detector, this K, has drifted from its nominal value. Now the KVCO itself is not constant, and it may be that in some situations it just doesn't meet the locking condition anymore. The loop is just not stable anymore. That is possible. Now I know I've talked about that I'm going to do a video about PLL theory, which would make all of this make a lot more sense, but for the time being, the value of this K and the value of the KVCO plus a whole bunch of other parameters fit into the feedback equation of the PLL and is very important for its stability. So maybe it has drifted and it just doesn't work across the entire range. It's a bit of a long shot, but it is possible to try it out. Now I did find a spare board, but it has one of these on it. I have no idea if that one works or not, but I may be able to just replace it and see what actually happens if anything changes at all. That would be another thing. Now, if you look at the block diagram of this thing, there's nothing really unusual about it. You know, you get the reference and the signal coming in. You have the up and down signals of the phase detector coming out, which you have to filter and then put it through a loop filter and so on. So all of that is really nothing really unusual about it. It's just made in gallium arsenide. So let's take a look at it. Let's see if we can remove it and replace it. So I have this donor board that I've been using and stealing components from over the years for various repairs. This is not from the same instrument model at all, but as it is often the case, Keysight and other companies reuse a lot of the architectures and components across different models because it's obviously more convenient and the architectures aren't always changing drastically. If you look carefully in the middle, you can recognize a very similar structure between the Fractional-N divider, FPGA, and the phase detector. So we're going to steal this phase detector and put it on the other board and see if it makes any difference at all. And there's a lot of other components in here if you ever need to steal some. In fact, I've taken some amplifiers from here and a couple of other things over the years. And through the magic of 4K television, here's the replacement. It did take a long time to do this. As you can see, the parts do have a ground at the bottom and a lot of heat was required. This is a big board with many layers, a lot of ground in order to remove that. And even after I did, one of the pads came off with it, and luckily it was a pad that's not being used. It's not exactly centered, but visually I think everything is soldered correctly. All these components had to be redone around it. Some of them may be a bit crooked. I was worried about this transformer and the heat applied to it can destroy the enamel and short it out. I did cover it as much with tape as possible, but you can see things are really, really close to each other. But yeah, this is the old one, and this is the new one. Let's see what happens. Okay, the unit's powered on. It still works at 2.5 gigahertz, so at least we haven't broken it anymore. But let's see. I can go up just 2.6, 2.5, 4, 3, 2, 1. It was okay here. 1.9, 1.8. Ah, look at that. It works. It is working. Here you go. 400, 300, 200, and 100. And it should go all the way to 6 as well. And let me check the screen. Yep, no fractional error anymore. That is fantastic. Of course, there's a lot of junk because it's not closed yet. Look at that. That is great. So yeah, so perhaps the gain of the detector had deteriorated to a point where the loop was unstable. This was a pretty subtle problem, I have to say. So I'm quite excited. Now, this doesn't completely mean it's fully fixed because we need to do some performance verification to make sure the phase noise and everything else is okay. But that is super promising. Let's run a self-test on it. And here's the instrument in sweep. Let's do that max hold just for the sake of completeness here and see all the tones appear throughout the band. Again, this junk will go away hopefully once we close it. And it should have pretty much everything. There it is. That's its entire frequency range. Some of the tones will get refilled again because it's not capturing every round. But yeah, looks good. Now the self-test will do a lot of things internally. It won't check performance verification, but it will check ALC, PLL across many different frequencies. It will do frequency hopping. It will check many, many parameters. So let's start with that because that's pretty important. Okay, so now for a self-test, utility, we go to instrument info, self-test, and complete self-test. This is going to check the arbitrary waveform generators built in, the DACs, and everything else at the same time. It's going to take a little bit of time, but there's an extensive set of checks it's doing. Okay, and the self-test looks indeed much, much better. You can see there are a lot of tests that are done in order to verify that this thing is working. So this doesn't still mean that we are completely in the clear. We need to measure the phase noise because the component we changed can directly influence the phase noise if it's not the right one. It's in the loop, of course. So let's hook it up to a phase noise analyzer and see what it does. So let's go ahead and measure the phase noise. I have set the instrument to 1.9 gigahertz output frequency, and that puts the VCO frequency around the areas that it used to be unlocked. We're going to use the Agilent E5052B, which is a cross-correlation signal analyzer. I have a complete video on what cross-correlation means and how phase noise measurement is actually done, so definitely check that out. And we have a plot over there, and we can compare that with a plot of a data sheet of this model. And I couldn't find exactly the year because this is a fairly old model, but nonetheless, it should be pretty close to what this data sheet says. Let's take a look. And here's side by side the measurement of the phase noise from the data sheet here on the left and the measurement that I just did. Now I'm making this measurement at 1.9 gigahertz, as you can see over here. That matches this curve, the blue curve here on this plot. And the reason is because this is where the instrument began having these issues. And remember, the VCO is running at half this frequency. So if you look at this blue curve over here, and we can compare it with the decade of the phase noise here on the right. So at around 10 hertz offset, you can see it's around minus 52, and that's exactly what we have also, minus 52 dBc per hertz. At 100 hertz, it is going around maybe minus 95, and here we're actually a couple of dB worse. We're about 4 or 5 dB worse. Same at 1 kilohertz, it should be about maybe minus 105, 106. We're at minus 100. At 10K, we're only 2 dB worse, and then afterwards, we're actually better than the datasheet. So I'm not exactly sure if that's really the problem from the instrument, or it's just that this datasheet isn't exactly matching the model that I have. Also, keep in mind that this is a pretty old unit. So our phase noise is a little bit worse here. It matches here, and is actually better here. So I would say that this is fine. For all intents and purposes, for this unit, it's functional. I should also probably go back, open it up, and really tighten the chassis and the really shield, bring it down, make sure there's nothing that's deviating these. Remember, these numbers are already pretty small, so you can imagine that even a very, very small amount of leakage and problems in the loop can introduce this. Now, I think from the shape of this, it looks like the loop filter band is around here or so. So this really is the reference multiplied up, so it should be pretty good. And there might be some aging effect on that as well. And there you have it. I hope you enjoyed this repair and analysis of this unusual failure mode of this synthesizer. If you like this kind of content and want to support the channel, it's really easy to do through Patreon and PayPal. It only takes a few minutes. And of course, subscribing and commenting helps the reach of the video to a wider audience. It's also kind of cool to see how, as Siglent has introduced more and more equipment, we can make all of these measurements basically entirely in their ecosystem of equipment. I have a really cool end-to-end measurement metrology video directly using all of their instruments to make a fairly complex measurement. That's going to be ready in about a month or so, so please keep an eye out for that if you like to see what's going on. As always, let me know what you think in the comment section, and I'll see you next time.